Hi, I'm Alexander, and this is Scary Stuff Metaprogramming, which is basically a showcase of the metaprogramming capabilities without doing any macros. So let's get right into it. About me, I've been a Scala developer for the past 4 years now. I'm mainly working with backend systems, and in my free time, I usually do OSS. Basically, I am the creator and maintainer of one library. It's called duct tape. As Matilda said earlier, it's about data transformations, and it mainly relies on macros. And then about the talk itself, it's loosely based on this blog post I created like 2 years ago. It's called Inline Your Boilerplate, which once again basically talks about the same things we'll be talking about today. So metaprogramming without any macros. But the problem with that blog post is it's kind of outdated right now. So there's a lot of stuff that has changed in the last 2 years. Basically, the match type spec got rewritten, and some of the match type tricks don't work anymore. And there's also some new stuff like selectable and named tuples. Sorry, the interaction of selectable and named tuples that allows us to make some even cooler stuff that we see later on. So yeah. Let's go into the agenda. And there's only 2 things on the agenda today. So there's a quick walkthrough of the toolbox, so the things we'll be using, the things we want to be using. And then a live coding session where we'll be creating like a small library that does case-class transformations, like compile time safe ones, but without macros, basically. So yeah, let's get right into it. So first, there's the iceberg of complexity of metaprogramming. So there's the tip, there's the shallow depths, and there's the abyss. The tip is what we'll be looking at today. So this is all of the things that are not macros, but are still like compile time, type level adjacent. And then the shallow depths and the abyss is basically macros, but make like levels of macros, lightweight macros, and then the heavy AST stuff. So let's go through all of the stuff that I consider that are at the top. So that is literal type, the Scala compile time package, mirrors, match types, selectable, and named tuples. So let's go right into it. First of all, literal types. So basically, type of a literal value. So you can imagine that you have a string that's literally I'm a literal type, and that string actually has a type of I'm a literal type, like represented at type level. Literal types are present for all of the primitives we have, so your ints, longs, floats, whatever, and plus strings. So as you can see, that also works for ints, that will also work for longs, whatever. We use them as a means of like passing information in our like type level computations, because literal types are used, as you will see later on, to encode, for example, case classes field and field names, things like that. And there's one thing that bridges the compile time word and runtime word for literal types, and it's called value of. Basically, a special case compiler generated type class that materializes values of literal types at runtime. Sorry, that materializes value of a literal type, but for use in runtime. So if I summon value for this thing right here, right, I get back a string of I'm a literal type, but at runtime. Then we're following up with match types, which are basically type level functions. So they allow us to pass types in and get types out. Basically, they allow us to compute types for use later on. As an example, there's this little thing here that takes 2 tuples as arguments. It first zips them and then maps over the resulting tuple. And whatever is inside the pairs that we have will be wrapped in an option. So if you squint hard enough, that basically looks like method calls, but maybe not method calls, maybe like procedures, more like. It is actually what it is, right? So an example invocation of that looks like this. For those 2 tuples would yield us a tuple of options with those types matched together. The tuple component object is of a special interest for us because the match types present there basically form a collection library of sorts for working with tuples, but at a type level. Because as you know, tuples in Scala 3 are actually encoded as HLists. So basically a cons list, but for types. So there's all of the operation that we would expect you would see on a list. There's map, there's flat map, there's fold, there's reverse, whatever, all of that. But for us to use at type level. So yeah, you can see that the tuple companion object provides a collection type array of sorts. I'm probably repeating myself. Of course, nothing stops us from declaring our own match types. They can be recursive, they can be whatever. There's a lot of stuff we can do with them. You'll see later on. And then moving on to the Scala compile package, which is a set of compile special case primitives, especially tailored for compile operations. So for example, summon all, which is a special method that given a type of a tuple of type classes, it will try to materialize all of them. So for example, here, I'm mapping over a tuple of literal types. I wrap them in value of, and then yeah, that basically gets summoned. I turn that into a list. I then call value on that list and get the values back. There's a comment that asks if shapeless is needed with Scala tree. Yeah, it's not needed. Exactly. And for this special use case, there's also like a shortcut basically. It's called const value tuple. You just feed it a tuple of literal types, and you get back a tuple of those types. But at runtime, you can turn that tuple into a list, which, as you can see, results in exactly that. So we'll be using that as once again a bunch of primitives that we'll be using for transformations later on. And then they mesh very well with match types and literal types, as you can see here, for example. And then we move on to mirrors. So what is a mirror? A mirror is a way of representing coproducts and products, like information about coproducts and products, but at compile time. We'll be only looking at products, so only showing that example here. So for our example case class like this, that has three fields, it's called int, string, and list. A mirror for that would look like that. So you can see a mirror for that got summoned, and that's and the information about the case class itself is represented as type refinements, actually. And why is that? Because that information is needed for us at the compile time level when we do type level computations, but not at runtime. However, that can actually be like bridged over from the compile time level to the runtime level, so nothing is lost. So for example, the labels are represented as a tuple of literal strings. The types of those fields that map to those labels are represented as a tuple of types. And the name of the type itself is once again a literal string. It also provides a special from product method that is pretty low level and not really type safe, but it basically abstracts over constructors for the case class it mirrors, more or less. So for example, if I call the from product method from that mirror I summoned here on a tuple of those values, I will get back an example, like literally an instance of example with those those values from that tuple pasted in. So there's mirrors. And then there's selectable and named tuples, or rather the interaction between them. So named tuples are an experimental feature in Scala 3.5, I believe. And they're just like tuples, but they have names, right? So you can create a named tuple just like that. Actually, that's actually just a type, not a value. I messed up, sorry. Just imagine it's a value of that. And then you can call to those names like you would call on a case class, for example. Of course, calling fields that don't exist doesn't work at compile time. And then there's the interaction with selectable. So selectable, now if you provide a type called fields in selectable, that will actually be represented as the set of fields you can access from that selectable instance. So if I provide a type of fields for this specific selectable that's called selector, and this will be called that, right? I can call selector.int, I will get the value back. But of course, if I call selector.main.think, that will fail to compile. And we use that for configurations later on. I'll show you. It's very cool. Okay, So for the stuff that we won't be using, just a quick showcase, really. So these are basically the shallow depths, I call them. And these are like lightweight macros. So basically what I mean by that, a lightweight macro is a macro that only operates on two types, exp and type, and only does, more or less only does pattern matching on code blocks and types. So that's a quick macro that basically materializes literal strings from literal types from a tuple of strings. Yeah, it just does that. I will not go into the implementation that we've got enough time. So this is how it looks like with the lightweight macro approach. And then we go to the Abyss, which basically operates on the ASTs. These two things do the same thing. Basically, they materialize a tuple of literal strings into runtime values, as you can see. But the difference between them is that this approach here is actually more or less compatible between versions, so that you know that stuff written this way will probably not change in a minor bump of the compiler, whereas ASTs are pretty low level and they're not guaranteed to be compatible between versions. So it can be quite tricky to work with them sometimes. But yeah, that's just a quick showcase of this stuff we won't be using. Okay, so now for the live coding part. So as I said, we'll be building a small library that does case class transformations, and we'll be building that in levels. So there's 3 levels to that. The first one, basic, and these are basically transformations for case classes that share the same names or the same types, and are not extensible. Basically, a warm-up. And then the intermediate level, where instead of where the field names still need to match up, but the types that are like typed to those field names can be different, and will basically be summoning a typeclass instance, a transformer actually, for each field or for each field pair for a given type, and that is actually user extensible because a user that uses that can provide an instance of that typeclass of transformers for each type. And then the fancy level is basically where we building a builder of transformation of sorts that will allow us to build out transformations that are not quite possible automatically. Basically, it will allow the user to, for example, fill in the blank fields from for a destination type. So you'll see later, it's really cool, as I said. Okay, so for the basic example, we have 2 case classes here, album and ever so slightly more detailed album. The only thing that differs is this additional field. So the end product should be able to convert from a detailed album into an album because it has less fields. But it shouldn't be able to do that in the reverse order, basically because it doesn't have enough fields to fill in all of the fields of this, right? So this should fail to compile, and this should just work. And to do that, we just need to check if the source has a superset of the destination fields. So yeah, so let's try that. Okay, so that's the same example as you saw on the slide. And there's a quick test here that will allow us to actually see what is happening. So first of all, to check the relationship between those fields, we need a way of representing the fields at some point, I guess at compile time, basically. So to do that, we'll create a class called field with 2 types, the name and the type itself. And that won't be represented at runtime. We just need that from compile time. And the thing that will allow us to actually run those quasi set operations would be the subtyping relationship on intersection types. Let me show you. So for a source type, that would look like field of field1, for example, and that field has an int, and then a field 2, which is string. Let's try a destination type as well. That has 2 fields, but the field order differs. So field 2, and that will be string, and then field for field 1, and that will be int. And now, if I do source is a subtype, if I check if source is a subtype of destination, that would actually not fail, that will actually succeed, because these are basically the same types, right? But any moment I change the label of a field like this, that stops compiling, right? I could even change the type that's represented by this. That also stops compiling because that doesn't hold anymore. And if I add more fields to the source, that will actually still work. So if I add a tiered field, that would be a list, for example, that still works because it still has it's still a superset of those fields. So yeah, given that, we know how we actually want to approach this, and how do we do that? So first of all, we need a way of obtaining fields for all case classes. So to do that, we'll create a match type called off, field.off, that accepts the tuples. And so actually that would be the labels, which is tuple, and types, which is also tuple. Okay, so we know that we have our labels and our types. Now we just need to smash them together. So to do that, we would do tuple.map, and then first of all zip the labels and types, and then use that and the thing that we got out of it to pattern match in that. So we know that zip always gives us pairs. So it's a label and a type, and we just turn that into a field. If you look, once again, if you squint hard enough, this basically just looks like your run-of-the-mill functions or procedures. Okay, so now that we know how to get a tuple of fields for each case class, let's try doing this here. Oh no, actually, okay, yeah, we find ourselves with a tuple of fields, but a tuple is not what we need. We need an intersection of those fields, right? So we just create another match type. Let's call it intersection that accepts tuple, and we will just fault over the tuple. So any, because any is the 0 element of an intersection type, and then we have our current and our accumulator, and we just do current and accumulator. Okay, and all of that is already in place. So the only thing we need to do here is to create this little concoction, basically. So we'll be looking for an intersection of source.mirrored ln labels, source mirrored ln types, is a subtype of, let's go all the way here, is a subtype of fields of the destination types fields. So dest mirrored ln labels, dest mirrored ln types, right? So let's see if it actually works. That will still not work, but I want to just see if the compile time check that says will actually work. So transforming a detailed album into an album actually still compiles. That doesn't work, but it still compiles. So doing that should give us our compile time error. Great. That error is pretty scary, to be honest. So we can make it a little bit nicer if we use implicit not found. So try that. So sources fields are not a super set of destinations fields. Okay. And that error message is much more tolerable. Okay, so now that we have the compile time check done, we are free to do some crazy stuff at the runtime level. So let me just copy and paste one quick line here. I will go through it in a moment. All right, cool. Okay, so I just copy and paste on my implementation. Let me go through it. So first of all, I ask for the source to be a product because I need some of the methods that are only available in products. So first of all, I get all of the product element names from the source. So that's basically the fields of the case class. And then I zip that with the values of of that source, of that case class, yeah, and turn that into a map, which results in a map of string and any, which is not very nice of a type description, but having this, having that, we are sure that all of the elements from source are actually available, sorry, all of the fields from destination are actually already in the source, right? That's the whole point of doing that here. Okay, and then to complete our transformation, we need to grab the destination labels. So we do that using const value tuple. So we materialize those labels, we turn them into a list, and then we cast that list to a list of string. This cast can be actually avoided, but that's additional couple of lines I want to go into. I can show you that later if you want. But basically, we find ourselves with a list of strings, and that list of strings is the fields of the destination type. So the last thing that is left for us to do is iterate over all of the labels of the destination type and grab a value from the source, give under that label. And then we use the from product method from source, from the mirror, from destination's mirror. We feed it a tuple that we create by doing what I just said. And yeah, and that's really it. We already get, and then we get an instance of the destination type, just like that. So, okay, that still doesn't compile because it's not meant to compile. Let's try running it. That's the basic test. Yeah, as you can see, the detailed album, this one, actually, this one, got turned into this. Like here, it was printed here, and then the assertion did not fail, which means it's equal, right? So great. These are all basic transformations out of the way. Let's go back to our presentation for a moment, and let's go through the intermediate transformations. So basically, they are more or less the same, but the one thing that changes is we are not sure that we cannot be sure that all of the types all of the types that match like name-wise are actually the same type, right? So we need a thing that will allow us to convert between those types, and that also needs to work at a compile time level. So the answer to that is actually a type class. So we'll be summoning a type class instance for things not super out of the box. So let's get right into it. So intermediate transformations. Once again, the same example as the one just shown on the slide. And what we need to do. So first of all, we need our type class. That's going to be a transformer. So our transformer is just a type class that has two type parameters and a single method called transform, and it transforms the source value into the destination value. It's a total transformation, so it should not fail at runtime, right? And I've given it a single instance for identity transformation. So if a type is one thing, then it needs to be the same thing in the destination. But still, our user is able to provide their own instances of a transformer. Okay, so now how are we going to actually make it work? So let me just copy that because I need that here. Yeah. So how are we gonna like map the fields from the source to the destinations fields? So we'll use a match type. Let's call it field-wise transformers, and that will accept two tuples, a source tuple of fields and a destination tuple of fields. And the implementation would look like that. So we will actually be going through the destination elements, actually mapping through them. So we map over dest. We know that A is supposed to be a field. So it has a label and a type. And the question is what goes here, right? So for now, that will be nothing because we don't have implementation of it. But we need a way of, basically, we need a way of searching the source tuple for a field with this label. And to do that, we are once again create a match type. And let's call it type of. And that will accept two arguments. So that will be the name and the fields that we'll be searching on, which is a tuple. Yeah, and the intention of that looks like this. So we match over fields. If it's a field of a name and some type, and we still need to remember that we're matching on a tuple, so we need to deconstruct it properly. So if we know that the field that's inside is the same type of passing here, we can return the type that corresponds to that field. So we just do that. But in cases where we don't, we deconstruct the tuple and recursively apply it on the tail. And there's one case where I don't really handle here, so that's the empty tuple. And that's because I don't want the empty. So if there's an empty tuple, that means there's no match, right? So I don't want that match type to be reduced. Ergo, I don't want the compilation to succeed if you had the empty tuple case. So I basically don't provide it here. It's like a match error, but at a compiler level. Okay, so having that, we need to map all of the destination fields to a transformer type. So we can do just that, right? So transformer, and then that's gonna be TPE is .tp, so that's the destination type. So this is the type we are mapping into. So we need to find the type from the source tuple that has the same name as this. So we use type of label and source. Boom, and that should give us the tuple of transformers that we need to summon to get a proper transformation. Okay, so let's try writing this down. Back here. So first of all, let me declare my source field, which will be field of source mirrored element labels, source mirrored element types, and my destination fields, which will be field of source mirrored destination. Oopsie. And then the mirrored element types, yeah, like that. Okay, so I've got my fields here, and then I need to summon all of the transformers. So I do transformers, I do summon all, and we'll be using the same match type we just created. So field-wise transformers, we feed it the source fields as the first argument, and then the destination fields as the second argument, and that's really done. I already have my transformers summoned here. So I just turn them into a list, and suddenly I need to cast them here as well. There will be a list of transformer any to any. Okay, now that I've got my transformers, I need the destination labels once again. So const value tuple, there's mirror element labels to list. And once again, we cast that to a list of string. One thing that, another thing we're missing, so the erased source. So that would be self product element names, zip that with self product, what is it? Oh, product iterator, yeah. Product iterator, and then turn that into a map because we still need to use that value. So we've got our source as a map of fields to values, and then we just need to zip the labels with the transformers. So you remember that we are actually going through the destination fields. So we are sure in this way that the order of those transformers here actually match order of the labels. So we can just create a transformer map. Which will be destination labels zipped with transformers turned into a map, and that will give us a map of string to transformer. And now for the last part will be just from product. We need to feed it a tuple once again. Let's create an array, and that will be an array of any. And yeah, we just go through the labels. We map over them. So label. And first of all, let's grab the value from the erased source. And we are, once again, we are sure that the values are there, because otherwise, wait, that this line will actually not compile. I will show you later. So we are sure that they are all there. Value, source value will be erased source of label. Okay, we get an any up. Okay. Right. We get a value, then we need a transformer. So transformer map. Let's grab that. Label. This is a transformer. So the last thing to do is just to apply the transformer to the value. Transform source value and turn the result into an array. Boom. That should just work, right? Okay. And let's get back to our example. So as you can see here, the case classes we operate on, they are the same, but the release timestamp is a long in one and instant in the other. So now that doesn't compile because there's no instance of transformer for long and instant. So let's give it an instance for that. Boom, that should work. And now the other way around doesn't compile because there's no transformer from instant to long. So once again, if we just provide a transformer, that should just work. Okay, so yeah, that works at compile time. Let's see if it works at runtime. Let's try running that, and that will be the intermediate test. Boom, just like that. That actually got transformed, and the assert did not fail, as you can see. So it's as expected. Yeah, so these are our like intermediate transformations for like type class derivation between case classes. And there's one last level that's left for us to explore, which would be the fancy transformations. So an example of that would look like that. So we are back to the original example of albums, but this time the larger case class of album has 2 additional fields. And the end product is supposed to work like that. So we are still able to convert from a thing that has more fields into a thing that has less fields. But now we are also able to convert from a thing that has less fields into a thing that has more fields by providing those fields, like filling in the blanks, kind of. And it's all supposed to be compile time safe still, right? Okay, so let's try that. And that one actually will not be live coding because there's a lot of code here and I probably would run out of time. So let's go through the code that's already built for that. All right, so first of all, the test, the end product. Let's look at this. That's the same case class set that we saw before, the same values. And okay, so converting from a detailed album to an album still works. And then converting from an album to a more detailed album, that still works because we put in the field. So if I comment that, yeah, that doesn't compile anymore, right? The error is kind of scary. I've got to admit that, but yeah, it still works. And I need to provide the correct type here, so it's all type safe. This error is actually nice. Yeah, so it works just like we would like it to work. Let's see if it actually runs. As you can see, yeah, it runs. As much as you can read from that, it's kind of not readable, but yeah. So how does it work? Yeah, how does it work? So it's all backed by a single class called builder that has like a whopping 7 type parameters. I swear I need all of them. It's got a source type, the destination type. It's got a source field, so it's a tuple of fields, as we saw before. It's got a tuple of transformer destination fields, which is a tuple that we'll be using for summoning transformers, just like we did in the intermediate example. And then we've got our configured destination fields that will be the fields we configure, basically this, right? Yeah. So first of all, let's go through how the withField method actually works. So the withField method accepts a function from selector to a field that basically is the selector of the field, right? And how it works in this case is selector. We give the destination names and destination types of the selector here. So a selector is a selectable class, and it's got the tuple of names and the tuple of types. And we build out the fields type from that. We basically build it out to let me show you, a named tuple of names and the fields corresponding to those names, right? So this will allow us to, and then implementing select dynamic on that will allow us to pick the fields we need, and we also will get the name of the field available to us at compile time here, but we also will get the field at runtime as well here, because this will just get passed into this. And field, the definition of it kind of changed, because instead of being like a purely compile time construct, it's also got the name value written into it. So yeah, that's all there is to the selector. And its usage looks like that, as you can see here. So I can one more thing I need to show off is I cannot just make fields up as I go, because that will not work. Yeah, and once again, the error here is not very great, right? But it works. Yeah. So the field we feed method. So we got our selector that gives us the field, and then we feed it a config. Config is just an enum. It's either a const or a computed. I only showed off const, but computed is still possible. So const is just you provide a value that will be then placed into that field, and computed gives you an ability to map from the source tab to that value to a given field. Yeah, and the implementation of with field is really just grabbing the field from the selector, so applying this function to a selector we build out here. That will give us a field of something, and then we just put that the field, or rather the field name and the config itself that's fed in here into this map right here, right? So it's all like kept at runtime. And then what this actually returns is a with config type. So it's still a builder, but with a bunch of modifications. So these fields, this is all copied over, but what really changes here is the transform. We remove an instance of a field from the transform destination fields tuple, and we prepend an instance to the configuration of destination fields tuple. I know that's complex. Sorry, I got not a lot of time. So yeah, that's really what changes here, and that's what enables the transformations. And then at the end of the day, when we call transform on that, first of all, that will try to transform all of the transformers that are all the transformers that are mapped to a given field with this. So there's one more thing that we've changed here. It's basically the same thing we did with field-wise transformers, but instead of building just a transformer, we build out a field transformer, which is basically a transformer with the field name written to it. And it's got a derived method that will always materialize that field transformer, given that the name is actually a literal type, and there's a transformer for those two fields. Yeah, let's go back. So I materialized a tuple of field transformers for all of the fields that I will need my transformers for. I then turn that into a map of field name to a transformer, and then it's business as usual. Basically, we go through all of the destination labels. So we first grab the destination labels. We then get our erased source, and then at the end of the day, to actually resolve the values, we go through the destination labels. So we try getting a transformer for a given label here. If it's there, we grab a value from the source by the given label and feed it into a transformer, just like that. But if it doesn't exist, then we are pretty sure, at compile time, basically at the runtime, that there is a config for that field. There needs to be a config for that field. So we just feed it into the configs map that lives inside this class, right? And we grab a config from that, and we just match on that config. It's either a const or a computed. If it's a const, we just get the value back. If it's a computed, we feed the source value, so the very source value, into that function, giving us the value back. And at the end of the day, we get our destination values, and then we just call dest from product. We build out a tuple, turn these values into an array, and we get out our destination type value, right? And once again, the working product just works like that. It allows you to, it's compile time safe, and okay. And that will be all of the live coding all of the way. So yeah, a summary. I would say that doing metaprogramming without macros still is basically can get us pretty really far. With one thing that's maybe not as nice is the error messages, right? Even still, that's very, very, very impressive. At least I think it is, because this stuff is basically available all of the box, and we can do anything we really want with it. And also, I know I just spent the last 30 minutes talking about not using macros, but macros are still there and ready to be used if that stuff doesn't meet your needs, right? So yeah, that's it. These are the resources, actually a single repository with all of the code we've seen here. So go look at it if you want. And that will be it from me. Thank you.
Thank you, Oleg, for the presentation. And there are some questions on the chat. So,
okay, I see. Yeah. So first of all, so shapers is not needed. Okay, yeah, I've answered that one. So if it's possible to generate case classes automatically somehow, no, sadly, not really. The best you can do is generate named tuples, and then along with the things available with the interaction of named tuples is selectable. That gives you a lot of headway, but still it's not possible to generate case classes sadly. Okay, another one. What would be the recommended way for reading or learning materials such as books? Yeah, that's the point really. There isn't much material available, and I try my best. So basically, the best thing I can actually give you is let me pull it up. Macro examples. There's a moment. There's a whole repository. Can I join the chat somehow? I cannot join the chat. Sorry, but basically, I can probably show this. There's a whole repository. It's called .macro examples. It lives under lampfl. That's full of examples for macros. Not really match types and the things we've just discussed, but basically macros. And I think I've learned the most from this single repository because it's got stuff from basically everything you want. If it's not there, you can always ask on the Metaprogramming Discord of Scala 3. I try to be active there. There's other users there as well, always answering questions. So that's really the best I could give you for this specific question, sadly. Okay, yeah, and I think that's it, unless you have some other questions. Oh yeah, okay. Okay, yeah. So first of all, what drove me to write duct tape? When Scala 3 got released, Chimney kind of looked for a moment abandoned. There was no, literally no, there was no activity on the repository for a year or so, and I just thought that that's it. Someone needs to step up, right? Because I wanted to. I've had a bunch of projects at work that I wanted to migrate to Scala 3, but basically Chimney was the biggest hurdle for some time. So I just basically wrote my own. But yeah, but currently Chimney is actively maintained. It's got a bunch of more features than duct tape, and it's more battle tested, I would say. So yeah, but these two libraries are both great, I would say. So pick whichever you want. And then is duct tape more macro or higher level stuff? So yeah, duct tape actually started out as very, very high level stuff, like the things I did here. The whole blog post actually that I showed you at the very beginning is about actually that 0.01 version of duct tape. That's how it worked in the beginning. But then as time went on, I gravitated more towards macros more and more and more. And now with duct tape 0.2, it's all macros because basically the biggest advantage of macros is it allows you to inline code without really any runtime stuff like wrapping stuff in functions, etc. You just inline code basically in a macro, and it looks like a code you would write down manually. Whereas what we did here, all of the runtime semantics, for example, grabbing stuff from a map, things like that still will actually run at runtime, right? So there's some like performance stuff to worry about there. Yeah.
Okay, and I think this one is for me. So no, not now. Now we are looking for someone who would like to work full-time.
Yeah, another question. How long did it take to implement that? Okay, so the first version, the one I described in the blog post, it didn't really take that much time. The implementation phase, like it was more like testing phase really to see how far can we push match types. I can push match types in typeclass derivation. But once I got my footing in that, writing it down was pretty easy. Then rewriting that in macros was once again a little bit of a change, but not that much. But still, it's been out there for I believe it's like 3 years now, and it's been already rewritten twice. The latest version published in I believe February was the newest one, so 0.2. We're at 0.2.5, I believe. I'm working on 0.6 at the moment. But still, it's just a part-time job, right? So sorry, not part-time, just off-work job that I do because I actually like it. And yeah, if you were to say that like for like 8 hours a day, you'd probably be done in like a week or two.
Yes, this video will be on our YouTube channel. Okay, are there any more questions?
Yeah. All right then. Thank you for hearing me ramble for the past almost an hour. Hope you have a great day or night. I don't know which time zone you're in. It's pretty dark here, so yeah. Thank you.
Thank you, Oleg, for presentation, and thank you all for joining.